Good morning to all. This is Shalya from ECE department. So now in this video we are going to discuss about the rectifiers and filters. Already we are discussed about what is rectifier, how they are functioning, some of the definitions related to the rectifiers and what is filter we are discussed in this video. First we are going to discuss about the rectifiers. So what is a rectifier? Already we know that rectifier is that which converting the AC signal into pulsating DC. So those will be called as a rectifiers. So in this rectifier we have the different types of rectifiers, that is half wave rectifier, full wave rectifiers and bridge rectifiers. So depending upon advantages we are using different types of rectifiers in different applications or different circuits. So now in this rectifiers we are going to discuss about the some of the definitions related to the rectifiers. In that first one is ripple factor. So the output of the rectifier is not pure DC. It contains both DC components and AC component. That is a part of AC signal. The AC component is undesirable and is known as ripple. A measure of such ripples present in the rectifier output is given by ripple factor. That means, so when we are using the rectifier to converting the signal into DC, it is not so in case of rectifier, so it is not converting completely AC signal into DC. That means some form of AC, some part of the AC signal is also present along with the DC signal. That some part of AC component is undesirable. So that AC component will be known as ripple. So the measure of such ripples present in the rectifier output is given by ripple factor. So ripple factor means, so the measure of ripples present in the rectifier output is given by the ripple factor. At the same time, next go for the rectifier efficiency. So efficiency means, so we can calculate the efficiency by the rectifier efficiency is defined as the ratio of DC output power to the AC input power. That means when we are calculating the any circuit efficiency, we are calculated from output to the input. That means the rectifier efficiency is defined as the ratio of DC output power to the AC input power. That means in case of rectifier circuit, so the input given to the circuit is AC, the output obtained from the rectifier is DC. So when we are calculating the output, DC output to the AC input, we can get the rectifier efficiency. Next one is peak inverse voltage. So peak inverse voltage is the maximum possible voltage across a diode when it is reverse biased. That means when the diode is connected in reverse biased, then the maximum possible voltage across a diode when it is reverse biased, it is called as peak inverse voltage. Maximum possible voltage across a diode when it is in reverse biased. When the diode is connected in reverse bias, what is the maximum voltage will be called as peak inverse voltage. Next one is voltage regulation. So it is defined as the variation of DC output voltage with change in DC load current. So the voltage regulation is, it is defined as the variation of DC output voltage with change in DC load current is known as voltage regulation. Next one is go for the comparisons. Already in previous session, so how the functioning of half wave rectifier and full wave rectifier we are learned. So now go for the comparisons of half wave rectifier and full wave rectifier. These are the sum of the parameters related to the half wave and full wave rectifier. So the first parameter is number of diodes used in the circuit. That means to make the connection of half wave rectifier circuit. So here how many number of diodes will be used. So the number of diodes used in half wave rectifier is 1. In case of full wave rectifier, we can use the 2 or 4 diodes. That means it varies with the type of circuit. That means, so when we are using two diodes, it will be related to the full wave rectifier. So when we are using four diodes, then it will be called as bridge full wave rectifier. That means depend upon the number of diodes. So when we are using one diode, that will be related to the half wave rectifier circuit. When we are using two or four, that is related to the full wave rectifier. Next parameter here is maximum efficiency for rectification. That means how much of a signal will be converted into DC. That is will be equal to the maximum efficiency. So the maximum efficiency for the half wave rectifier is 40.6%. In case of full wave rectifier, it will be equal to 81.2 percentage. Next one is basic refill frequency. Here F, that is supply frequency, is provided. So in case of full wave rectifier, 2 times, that is 2F. So the basic refill frequency is equal to the supply frequency in case of half wave rectifier. So the basic refill frequency in case of full wave rectifier is 2 times of the supply frequency. Next one is refill factor. So the refill factor is more in half wave rectifier, less in full wave rectifier. Next, voltage regulations. So in this voltage regulation, half wave rectifier, the voltage regulation will be good. So, and in case of full wave rectifier, better as compared to the half wave rectifier. So already we have discussed what is the discussed refill factor and voltage regulation. So when we are comparing this, so the refill factor is more in case of half wave rectifier, less in full wave rectifier. In case of voltage regulation, so the regulation of this half wave rectifier is good, but in case of full wave rectifier, it is better than the half wave rectifier. Next one is transformer utilization factor. Transformer utilization factor in case of half wave rectifier is 0.287. In case of full wave rectifier, 0.693. Already we have discussed what is transformer utilization factor in previous videos. Now go for the peak inverse voltage. Maximum value of supplied input. Here twice the maximum value of supplied input. That means the supplied input will be equal to the peak inverse voltage in case of half wave rectifier. In case of full wave rectifier, it will be equal to twice the maximum value of supplied input. In case of peak factor, half wave rectifier, it will be equal to 2. In full wave rectifier, that will be equal to 1.414. Again, same thing, that is form factor and average current value. Here transformer core saturation will be possible, but it is not possible in full wave rectifier, because in full wave rectifiers only we are using either 2 diodes or 4 diodes. In half wave rectifier, it is possible to connect the transformer at the input end. So these are the some of the comparisons between the half wave rectifier and full wave rectifier. So from these comparisons, the full wave rectifier is better than the half wave rectifier to convert in the AC signal into pulsating DC. So this is the completely about the rectifiers. So the first thing is what is rectifier. So how many types in a rectifiers? What are the factors we have to calculate in a rectifiers and comparisons among the types of rectifiers. So that means what is in simple words, rectifier means it will converting the AC signal into pulsating DC. So now go for the types of rectifiers. Mostly we can use the half wave rectifier and full wave rectifier. In this full wave rectifier, either we can use the 2 diodes or 4 diodes. Next, some of the factors will be calculated. That means some of the parameters will be calculated related to the rectifier. Based on these comparisons of these parameters, so the full wave rectifier is better than the half wave rectifier. So next, go for the filtering. So in this filtering process is to smooth out the output of the rectifier circuit. So in case of rectifier, you can get the output as pulsating DC. That is not exactly the DC output. So to get the complete DC output, we are using filtering. That means it smooth out the output of the rectifier circuit. So one of the most common filter is the RC network. One of the most common filtering circuit is the RC network. So look at the waveform or a graph in this picture. So the first one is half wave rectifier output. So next is half wave rectified waveform after filter. That means some filter is. So this is equal to the completely the output of the half wave rectifier. So this half wave rectifier output is given to the filter circuit. The filter circuit will smoothen the rectifier output. That means we can get the output of this filter circuit is like this. That means somewhat we can get the DC filtering. That means some of the ripples will be absent when we are getting the filtering. So next, but in case of ideal DC source, that means when we are connecting ideal DC, constant voltage with no variations in a time. That means ideal DC will be just like a simple solid line. That will be called as DC. But so in case of rectifier output, you can get the pulsating DC. That means some AC components will be present. So these AC components will be filtered out by using the filtering circuit. You can get the DC output, approximately DC output, that is called as a filtering. So the most common used filter is the RC network. Most commonly used filter is the RC network. Now go for the circuit diagram for this filtering circuit. So here is equal to the, here we are using half wave rectifier. So up to this, part will be equal to our rectifier circuit. So this rectifier output means that is pulsating DC output will be connected to the RC network R1 and C1. So this R1 and C1 network will be, our circuit will be equal to our filtering circuit. That means the output of the rectifier will be connected to the filter circuit. Here the filter circuit is RC network. This filtering output will be given to the load. So here the load will be equal to RL. So the output across this load resistor will be equal to A0 of T. That is equal to our required output of the filtering circuit. That means the input for the filtering circuit is rectifier output. So this rectifier output acts as the input to the filtering circuit. So the output of the filter circuit is which smoothens the pulsating DC output of the rectifier. That means we can get the approximate DC output. That is about the filtering, how they are filter the signal. Now we go for the next one is types of filters. There are the different types of filters. So those filters will be equal to shunt capacitor filter. So here types of filters. So the first type of filter is shunt capacitor filter, series inductor filter, L section, that means LC or inductor input filter, CLC filter and CRC filter. Here CLC means capacitor, inductor and capacitor filter. CRC means capacitor, resistor and capacitor filters. These are the different types of filters. Now so next one is full wave center tapped rectifier and capacitor filter with load connected. That means here we are using the filter type is capacitor filter. So the input for the capacitor filter is coming from the full wave center tapped rectifier circuit. So that means this part, that means full wave center tap transformer full wave center tap rectifier here is. So here we are using the center tap transformer. Again here we are using the two diode D1 and D2, and this up to this part will be equal to the rectifier circuit. So the rectifier output will be given as input to the capacitor filter. Here the capacitor will be connected in shunt. Shunt means parallel to the load resistor. So that's why it will be called as shunt capacitor filter. So this will be equal to our filter circuit. So across this filter circuit we are connecting the load. So across the load we can calculate the VL and IL. Okay, so that means So in case of shunt capacitor filter, the input for the filter is a full wave center tapped rectifier output. So here we are using the type of transformer is center tapped transformer. Now the output of this capacitor filter output waveforms with load connected is so almost which smoothens the rectifier output. That means in case of rectifier circuit you can get the output so mostly in like this. So this is equal to our rectifier output. This output will be given as input to the filter circuit. Then we can get the output is so V2C, C2D and so on. This is our output of shunt capacitor filter with load connected. That means here this part will be equal to maximum voltage. Okay, so the time period will be equal to this will be equal to our time period T1, next T2 and T3. So this will be equal to dotted lines will be indicate the rectifier voltage. So the solid line will be indicate the filter output. So that means so suppose so when we are giving the input, so the input for the rectifier circuit is AC. We are giving the AC input to the transformer during positive half cycle. So diode D1 is in forward bias, diode D2 is in reverse bias. That means at a time only one diode is switched on, second diode will be off. That means during positive half cycle, so the input AC signal will be passing through this diode D1, D1 to the capacitor, capacitor to the load across the capacitor. So that's how we can get the output. So that is equal to the pulsating output. So the rectifier output is, so up to diode D1, the rectifier output is like this. At the same time, during negative half cycle as input to the transformer, so diode D1 is in off condition, D2 is in on condition. Then the output signal is from the center tap to the diode D2 to the capacitor. That means the second output will be equal to, that means during negative half cycle, so you can get the another half cycle as a input. So this output of the rectifier will be given to the filter circuit. Then the capacitor will pulsate in the DC. That means the main function of the capacitor is so which blocks the AC signal. So that's why these signals will be blocked. Only this signal will be allowed by the capacitor. Finally, you can get the output as pulse. You can get the DC output from the filter circuit. Next, another type of filter here is pi-type filter. So in this type of pi-type filter, we are using the CLC. That means the way of connecting these three components, that is passive components, are connected in pi. That is symbol like a pi. So that's why it is called as a pi-type filter. In this pi-type filter, so before that the output of the rectifier output is pulsating DC. This DC output is given to the input for the filter circuit. That means here C1, C2 and L. So the input given to the DC output is given as input to the filter circuit. Here the filter type is equal to the CLC filter. Across this filter we are connecting the load. That means pi-type filter with load connected. So now go for the pi-type filter output voltage waveforms. That means when we are using the two capacitor with inductor will be connected in series. We can get the maximum DC output from this filter. That means maximum we can avoid the or eliminated the ripple AC components. AC component means ripples will be filtered out by using the filter circuit. Here the dotted lines will be indicating our rectifier output. The solid line will indicate the filter output. That means the average frequency of this DC will be equal to 0. So that means this is equal to our output voltage. This output voltage is across the filter, then it will be average load voltage. So that is the output of the pi-type filter. Next one is load characteristics for circuits with and without voltage regulators. So that means here when we draw the graph between voltage and current, voltage means here load voltage and load current. So then open circuit voltage means circuit 2 with voltage regulator, a circuit 1 without voltage regulator. That means, so when you are using the voltage regulator, we can get the maximum approximate value of the DC. But in case of without voltage regulator, we can get the slightly slope in the output variations. That means there is a small deviation between with voltage regulator and without load regulation. That means when you draw the graph between load voltage and load current, we can get the output. So here we can use the regulator, we can get the approximate or maximum 99.9% of the output is in terms of DC. But so when we are using without any voltage regulator, we can get the some deviation between the output load current and the load voltage. So this is the load characteristics for circuit with and without voltage regulators. So here Zener diode. So the voltage regulator will act as Zener diode will act as a voltage regulator. So here analyzing the Zener diode. So here analyzing a diode operating in the reverse bias region will show that the current through it remains essentially constant until the breakdown voltage, also called as avalanche or Zener breakdown voltage, is reached. At this point, the current will increase very rapidly for a small voltage change. That means when the Zener diode will be operating in the reverse bias region, it works as a voltage regulator. That means when you go for the regulator circuit of this Zener diode. So here first look at this. This is the symbol for Zener diode. So in case of PN junction diode, it is simply the symbol of Zener diode is like this. But in case of Zener diode, we can use the slopes at the end, at the negative end. So this negative end will be called as cathode. This end will be called as a anode. This is the symbol of Zener diode. So then the characteristics of the Zener diode. So that means when the Zener diode will be connected in reverse bias to the supply, then we can get the, so that means when we are connected in reverse bias, okay, so during, so here is equal to our breakdown will be occur. So here the breakdown means, so when we are increasing the voltage, okay, so the current will be almost essentially constant or there is a small variation in the current. So up to the breakdown voltage, once it reaches the breakdown voltage, okay, so there is a small variation in voltage, there is a large amount of changes will be occurring current. This region will be equal to the breakdown region, this I minimum to the I maximum. This region will be used as a voltage regulator. That means, so the current will be remains constant. The current will be remains constant. That means, so this will be almost constant until the breakdown voltage, up to getting the breakdown voltage. So up to breakdown voltage, it will be maintain the constant current, but once it reaches the breakdown, that means once it crosses the breakdown voltage, then there is a small change in voltage, you can get the large changes in current. That is, there is a rapid increasing in current with a small change in voltage. This rapid change in current will be used for utilization of voltage regulator. This part of this region will be used as a voltage regulator in case of Zener diode. This will be occur when the Zener diode will be connected in reverse bias. Reverse bias means the positive supply of the battery will be connected to the cathode of the diode and negative supply of the battery will be connected to the positive of the Zener diode. Then the way of connection will be called as reverse bias. So that means, so the Zener diode will be used as a voltage regulator in case of reverse bias. Now the symbol for Zener diode is, so this one is equal to at the cathode end, we can use the symbol just like a Z. Sorry. So at the cathode end we are using symbol just like a reverse form of Z. So this end will be called as cathode, this terminal will be called as anode. Just like a our PN junction diode, this Zener diode is also having two terminals. Those will be called as anode and cathode. So the only difference between the symbols of Zener and PN junction diode is, so in case of normal PN junction diode, the cathode will be like a, sorry, so simple solid line, but in case of Zener diode, it will be just like a reverse form of Z. This is the symbol of Zener diode. Next one is Zener diode terminal identification. That means here we can identify the anode and cathode. At the cathode end there is a simple indication. That indication will be marked with silver line. Here go for the practical how to identify the Zener diode means at cathode end. So you can get this small line. This is the line. This line will be either in the form of silver color. That end will be equal to our cathode. So reverse of that end will be equal to the anode. Next one is Zener diode VI characteristics. So VI characteristics means in case of when the Zener diode connected in forward bias, the working of the Zener diode in case of forward bias is just like a PN junction diode, but mostly Zener diode will be used in reverse bias as a voltage regulator. So that means already we have discussed about this. That means when you draw the characteristics between voltage and current, that is load voltage and load current. Okay, so in case of reverse bias, it will be called as reverse voltage and the reverse current. So in case of reverse voltage, when we are increasing the reverse voltage, so almost all the current will be constant, but until it reaches the breakdown voltage, Vz will be equal to called as breakdown voltage. Until it reaches the breakdown voltage, the current will be almost constant. Once it crosses the breakdown region, so there is a small changes in the voltage. There is a small change in the voltage. You can get the large changes in the current. So this will be equal to I minimum. This will be called as I maximum. So the interval between minimum to the maximum current will be used as a regulator of the Zener diode. These are the VI characteristics of Zener diode. But in case of forward bias condition, that means when the Zener diode will be connected in forward bias, so the characteristics just like a PN junction diode characteristics. That means we are increasing the voltage. So according to that, the current is also increased. That is the forward bias characteristics of a Zener diode. So the working range for practical working range of this Zener diode is from, so I maximum to the, so Iz maximum to the, here is Iz minimum, here is equal to the Iz maximum. This is the practical working voltage range of this Zener diode in reverse bias condition. That means after the breakdown voltage, we can utilize the Zener diode as a voltage regulator. So here we are using the Zener diode as a regulator. So in this case we are using either series regulator or a shunt. In this case we are going to discuss about the Zener diode shunt regulator. That means simple thing here is, so the Zener diode will be connected in shunt with the load. Then the type of regulator will be called as Zener diode shunt regulator. So the input for this regulator is, okay, so that is from the output from the either rectifier or a filter circuit as given to the input for the Zener diode shunt regulator. That means here the input given to this regulator circuit is from either rectifier circuit or a filter circuit. Here the diode will be connected in shunt to the load. So that's why it will be called as Zener diode shunt regulator. So the current here Is will be equal to the source current. Here source resistance. So the current entering into this diode will be called as Ij. The load current will be called as IL. That means the source current Is is equal to the sum of Zener current, that is Ij, plus sum of load current IL. So source current will be equal to the Zener current plus load current. So the output across the voltage across this RL will be called as regulated output voltage. That will be equal to our VL. This is equal to our shunt diode shunt regulator. Sorry, Zener diode shunt regulator. The input for this regulator circuit is from either rectifier circuit or a filter circuit. So now how to get the regulation of the Zener diode. This characteristics of the Zener diode is very useful for voltage regulation circuits. So the Zener diode provides an effective way to clamp or limit the voltage at a relatively constant value, thus creating a voltage regulation capability. Regulation means we can maintain the constant output or a constant load voltage or a load current. So the Zener diode, this characteristic, that means so the practical working range of this diode will be used as a regulation. So these regulation characteristics will be used for voltage regulation circuits. So the Zener diode will provide an effective way to clamp or limit the voltage at a relatively constant value. So that means this Zener diode will be clamp or limit the voltage at a relatively constant value, thus creating a voltage regulation capability. So that's why this Zener diode will be used as a voltage regulator. That means it clamps or limit the voltage at a constant value. So that's why this Zener diode will be used as a regulator. So this is about the filter circuits, rectifiers and the regulators. So we will go for the differences. That means rectifier circuit and filter circuit and regulator circuit. So here rectifier circuit means it will converting the AC to DC. That means pulsating DC. Filter circuit will be used to filter out the AC component presented in the output of the rectifier. So the AC output is filtered out from the filter circuit. We can get the DC. So this DC output will maintain constant by using the regulator circuit. Mostly the regulator circuit will be used as a Zener diode. Zener diode will be used as a regulator circuit. That means these three are interlinked. That means rectifier will converting complete AC signal into pulsating DC. Filters. Filter circuit will be smoothens the output of the rectifier. So the filter output will be maintained constant by using the regulator. This is completely about the rectifiers, filters and regulators. Okay, so in this case we will learn about the what is rectifier, what is filter, what is regulator. So mostly we are using the rectifier circuit are full wave rectifiers. So filters are pi type filters will be used, that is more advantageous than the other filter circuit, and regulator circuits mostly used as Zener diode. Zener diode shunt regulator will be used for regulation purpose. That means to limit or to maintain the constant value at the load, we are using the Zener shunt regulator. This is completely lecture about the rectifiers and filters. Thank you.